Software progress, an oxymoron. These are two words that contradict each other. We don't really have progress in our software. We'll take a look at this. So I'll start with the history of computer technology. So we'll start back at Aristotle's time, in which he looked at inductive and deductive methods to resolve problems. Inductive is it might be the proper solution, or deductive where, yes, it is. It's an exact solution. And we had John Dewey, who wrote How the Brain Works, and then Descartes, who said, I think, therefore I am, and Plato, who was the teacher to Aristotle, and then Socrates, who was the teacher of Plato. And they may have had some input into these concepts. And then Sir Isaac Newton in 1687 carried this thinking of solutions or looking into scientific issues with a scientific method. And then we have David Hume, who was a philosopher, who was a big advocate of Sir Isaac Newton's, and actually could have even met him. He was 16 when Newton died, but he was in the same era. Why I put him up here is because he was a friend to Adam Smith. Now this is my start for our computer technology, which was in 1776, in which he wrote or published the book of The Wealth of Nations. And in it, he described how to break up complex problems into opcodes, if you will. So an action. An opcode to us in computers is an action. Add these two numbers, subtract these two numbers. Okay, and that was 249 years ago. After it was published, Baron de Parnay took his idea and decided that he would use it to calculate navigation tables. That was in 1791. And in that, he would use the opcode and say, here's an add, and he'd do a 3-column table. And he'd put 2 columns of numbers and do an add, and then he would hire high school students to do the simple additions or multiplications. That way he could get human computers to perform what we do with hardware currently. Human computer operations. Then we have Joseph Charles built the Jacquard loom. Joseph's nickname was Jacquard 5, and he used punch cards to weave out extreme complex patterns. Charles Babbage in 1820 or so started building the mechanical computer, the difference engine. Now he went and talked to Parnay and to Charles about the loom and about the human computers, and he designed his mechanical computer with these two concepts. So this is why I take it back to Adam Smith, and possibly with some help from David Hume, because Adam Smith and David Hume were friends. And then in 1840, Ada Lovelace published the first program that we know about. I'm sure Parnay had hundreds of programs in 3-column tables that we never got to see, but I'm sure he did the same thing, which is, and Ada Lovelace's was a 24 by 24 grid table of values and operations. So you had 24 operations with 24 values with the results, and that was the program Ada designed, which is identical to what we have today in all of our compilers. Now George Boole, I put this in here just to give us a reference of time frames, was 7 years later, and he designed binary logic, which we use today. And then Konrad Zuse, who built in 1938 the V1 computer, later renamed as Z1, but originally it was a V1. But when the rocket came out, it had to be renamed, or he renamed it. ENIAC, The first electronic programmable computer was in 1945 for the war effort. And then Grace Hopper in 1952 completed the work on Flowmatic, which was a later redesigned into COBOL in 1959. IBM Fortran came out in 1954. And then the first computer that I worked on was the IBM 360 computer. And this was in key points with, and I used WAP4 Fortran. I was in the engineering department at the University of Houston taking Fortran. Start in history, in my view, of how we started software. And as far as I'm concerned, we haven't really come any further in our software technology or our hardware. Variations, yes. Technology-wise, no. So, in our current software technology, we have redundant single-purpose applications. So, we have billions and billions of applications that are single-purpose. So we have editors. And the issue here is that each editor stands on its own. So it's like spell check. You go into Word and it has its own spell check, and you go into something else and it may have another one. So we have redundant logic, and our different operating systems all have similar logic. Basically, an operating system runs an application, which is simply load the binary representation and set the program counter, and then swap it out. Anyway, so same way with mapping systems. I was in mapping and I told this story before, is I translated a lot of people out of mapping systems. Intergraph, Esri, AutoCAD, ProScan, CableCAD, GeoVision. There was about 40 different mapping systems. They were all redundant. 90% of their application was identical. And so that's what I'm saying. We have redundant systems, and they were all isolated. All of these applications are isolated and therefore could not share the information. So anyway, they were locked into those systems because the vendors of these systems would not publish how the client. And we have accounting systems, so every accounting system is different. It uses the same identical logic. It's just applied differently for different purposes. But accounting is accounting no matter what. Same way with mapping systems. Draw this picture on a screen. Have a line library to display lines. Have a font library to display characters. Have a symbol library to display symbols. So in actuality, all these systems are identical. And actually, when I was moving these systems, and this was IBM GFIS, which was electrical networks, and then a CableCAD, which was, again, networks and graphics and databases. And all these systems, I guarantee you there was probably only about, I'd say, 300 or 400 lines of code, literally, difference between any of these systems, even though they were completely different. And our video application, so we have all these different formats, and then our databases are all different and do different things, and all of our compilers, which do identical logic, there is really no difference in any of our compilers. And yet we have, I don't know how many compilers, and if you talk about compilers and all the scripting languages like the DOS batch files and the JCL job control languages and the DEC control language, DCL, and all of these different scripting languages, and we have 100,000 of these. We've got G code for CNC processing, and we have just about every application has some sort of script that it has to run to initialize and to store and retrieve information. And we have different printing. Anyway, we have billions and trillions of single-purpose applications. This is our current technology. Jane, which is a system I'm looking at, or I am building, I've been building it for the last 11 or 12 years, and What I want to do is has no redundant logic. So instead of 40 or 50 mapping systems, all of them isolated, so we can't share between any of them, all that logic is identical. We could share the information because there's really very, very little difference. A line is a line, a symbol is a symbol, a font is a font. And we can consolidate that into one absolutely perfect logic. So what we want to look at is compilable logic modules. So instead of having 1,500 different type of, just about every application that does mapping or drawing has to do their own visualization. We don't need that. We only need one. And that could be, okay, this is 3D, this is 2D, this uses this particular parabolic curve around fillets. And, there's only about 20, literally 20 styles of arcs, and 2 or 3 styles of circles. And anyway, there's just very, very little bit of logic that we're looking at. But we consolidate it, and we put one copy in there, and then we select out what we want. So we want logic to access all digital information. So we put this in. So we have one copy to access all binary structures, all computer languages. So instead of writing all these compilers, we only need one piece of logic to do all languages. It really is that simple. And all these computer scripts to do installs, calculate installs, do all my make files, and all of these different, all my client server technologies, all my emails, and all of these manual operations that we have in all of our separate isolated applications. We have all these scripts that we have to perform manual operations that are very breakable because of versions, and very, it's a never-ending battle, but we can remove and eliminate all that. And so we want access to all of our hardware devices, our prints, and our displays. And so we only need one non-redundant set of logic modules. A module is qualifiable. So if I don't need certain, let's say I'm building compilers, I could say, look, give me a compiler, a JavaScript compiler with the C# data declarations. We can do that. It's simply qualifiable. So we have qualifiable technology-specific logic. So if we're talking about editors, we qualify it. Okay, I want to be able to edit maps. I want to be able to edit music. I want to be able to thousands or millions of technologies that we'd like to display. And this would all be in one editor so that we could edit, molecules, designs, music. We could edit maps. We could edit math equations. We could, exactly as we would put them on paper. Same with mapping, so that we have only one, so anybody could put in any of their applications a map or some representation of a map or a chart or any other visualization tools, mathematics and chemistry, so we can do mathematics and solve linear equations and do integrations and derivatives. So we can do all the things that we're going to do anyway. Instead of having all these separate applications, we have one application with no redundant logic at all. We only have one copy. So we can do chemistry and all medicine and every other technology. So what Jane is, which is the system that I'm calling doing, is one infinitely large application, meaning that there's only one copy of the logic, and then you qualify what you want to do, the action. I want to edit a map. It's application development, so it's static and dynamic, load on demand. So basically, nothing has to be done until you actually do it. So if you say, read the employee table, I don't really have to read it until I actually use it. Well, show me employee 1 or the first 12. I only need to get one at a time, which I'm doing anyway. So do I really load the whole table? No. I mean, we optimize, and that's the whole thing. And it's qualifiable. What do we really want in our application? And this can be, like I said, dynamic, so that when you say it, it actually builds that application or that part of the application. Or it can be static because it's cached, simply put. Look, this doesn't have to be built every time when I say something, but it might be. You might change a way. In this particular case, for this particular customer, I have to tie in his contract, and it has certain requirements for me to do validation. It may have some manual processes, and it's user controlled, so every user can set his own context. I'm only working on in Texas, or I have to go from Texas to New Mexico, and the rules change. So we have information and logic sharing. This is what we want to get to. If we have the information and we have the logic to manipulate it, then we should be able to share that. And this should be transparent to the user and to the developer. And so speed of development in all of this is minutes instead of man-years. So if you want to create a new school management system, and so because information is shareable and logic is accumulative, there is an end to all development. This is simply a fact. Working toward any other computer technology is a wasted effort. This is my view. In our current technology, we're not getting anywhere. If I can do this by myself, literally, we build one editor, we build one mapping system, we build one pipeline integrity system, we build one school management system, and so on and so on, one banking system, which is qualifiable for you as a user. So you build it. You don't let some other company come in and have access to your logic, to your information. You own your own information. Right now, you don't own your information. You don't even own the hardware that you purchased. I bought a TV and it's sending out logging systems back to its server, and I don't want it to do that, and I don't think you do either. We need to move toward absolute control of our information. So anyway, this is my view of what change should be, what our software technology should be. Take care, and have a great one. Bye now.